So I'm going to go ahead and run you guys through my module 3. This is Topher. So I'll go ahead and let you guys see here the hand calculations for regression lab 8. You can kind of pause here at any time, take a look. And the same for ANOVA. So here you go, hand calculations for ANOVA. All right, so I'll just go ahead and jump in. So welcome. The data that I chose to conduct a regression on looked at body weight based on average, tire sizes based on average, driver skill level based on average, and all of those served as predictors for Y1, which said was lap times around a Formula One racetrack compared to the average. So I chose multiple regression for this because I felt that it was the best method to use for the data, given that there are multiple factors which I wanted to compare. And I wanted to use the current factors, body weight, tire sizes, and driver skill, to predict the future lap times for Formula One racing, like I said. Given these desires, multiple regression made can vary. There's an array of assumptions that are important to meet in order to have a good and complete model of what's happening in the data. For example, we can assume that there was not measurement error in recording the data, since I guess I can just promise you that the equipment was used to, that was used to record the data was on top of the line and calibrated specifically for this experiment. And because with the MRC, we assume that the error comes into the model itself, whereas in ANOVA, the difference is that we assume the error is in the groups, since we're comparing the group means to the grand mean. So another important assumption in MRC is that there's not multicollinearity. Based on the VIF scores, which you see here for Y1, X2, and X3, they were all very, very close to 1, which when the VIF score is close to 1, it's safe to assume that multicollinearity is not something we need to worry about. And so here you can see our data will not be multicollinear. Ran next, and that allows us to determine autocorrelation of the data. You can see that the DWT statistic is right about 2.18, we'll call it. Now, granted, typically anything over 2 might mean that you have underestimated the significance of the data. However, because this is so close to 2 at 2.18, I feel like you can easily say, and safe to say, that our data is not autocorrelated. So now, as you can see on this next slide from this data here, provided by the regression output, the only variable that was significant enough to predict lap times was this X3 variable, which I labeled as driver skill based on average. This means that both body weight compared to average and tire size based on average did not significantly influence lap times. Additionally, you can see that the estimate coefficient for X3 is about 0.471, which means that for all others held constant, each 1 unit increase in this coefficient of X3, there would be a calculated increase in driving times. Cortina discusses this further in his article, saying that since the coefficients for multiple regression are basically partial coefficients, there can be somewhat of an odd influence on the IV in question, or lap times for this example. He cautions that as beta, or if you have a beta that's about greater than 1, you've got high collinearity. So here you can see with the 0.471, we don't have to worry about that because we're not even close to 1 to begin with. So collinearity is not an issue. Additionally, the regression output gives you an R-squared measure, and King talks about this in his topic and the usefulness of R-squared, basically saying that for any one equation, R-squared can be considered a measure of the proportion reduction in error from the null module to the current model. Essentially, it's a measure of proportion with the variance that's explained. Given our relatively low R-squared of about 0.25, we can call it, we can conclude that while our regression seems to fit well, there are clearly some outliers here that would affect the relative fit of the line, and we want to remove those. So if you look at the normal QQ plot, you can kind of see here we've got 26, 30, and 14 is a big outlier down here. And based on this QQ plot, which divides it into quartiles, you can see that aside from 14 and maybe these two up here, the data looks to be largely homoscedastic, which is another assumption that we would want to have met for both MRC and for ANOVA. So Moving on, though, if you look at this plot of residuals and leverage, we can see that data point 14 is in fact having a huge pull on the data and on the regression line, which seems to be causing the issues with our R squared and the technical lack of homoscedasticity, despite what this would suggest. So while multiple regression and ANOVA both seek to predict a continuous outcome, ANOVA uses one or more categorical variables as opposed to continuous ones in regression. While some make clear distinctions between MRC and ANOVA, I think it's easier to think of them as two sides of the same coin. They both use the same model, but in different ways. It's important to note, too, that in both of these methods, the data are residualized and not raw. Like multiple regression, ANOVA has several assumptions that we should make sure are met. In fact, they're almost the same set of assumptions between the two. So as you can see with the data here, based on the fitted plot, the data is somewhat homoscedastic, and it gets pretty close. It's hovering within like 0.5 on either side. There's also an equal amount of data in each groups, which gives us the sphericity that we need to have met in ANOVA. There's 30 in each. It's also important to note that the data must be independent, unlike in regression. So since we're using car brand and gender to predict lap times, it's safe to assume that the samples are independent. By looking at the ANOVA output up here, you can see that for F2, or car manufacturer, right here, we do have significance at 0.025. However, the p-value for F1 at 0.611, or gender, is not greater than 0.05, so we would fail to reject the null hypothesis and cannot say that this is a predictor of lap times. Additionally, in the residuals versus fitted plot, again down here, also indicates again that we're pretty close to being homoscedastic. So if you take a look now at this box and whisker plot that I did to plot the data, you can see that Ferrari clearly results in the fastest lap times by mean. McLaren isn't significantly different from this, even though it has the possibility for better lap times. You can also see, though, in the variance that even though it has the possibility for like really, really good lap times, there's also the possibility that you'll have really significantly bad lap times as well. This could speak to the newness of McLaren as a supercar company. They haven't gotten their formulas down. However, as for Lamborghini over here, you can expect slow times around the track from this car company who seems to kind of aim for the form over function motto. And then I went ahead and ran post hoc pairwise t-tests using the FDR, I guess, adjustment. And it revealed that while the variance is vastly different between Ferrari and McLaren, the means are not significantly different, which would mean that either one of these car companies would be fine, although I think I would choose Ferrari personally. But for the Lamborghini lap time mean is significantly worse than both McLaren and Ferrari. So again, you could choose either McLaren or Ferrari, but I personally would choose a Ferrari. So thank you for listening. I hope you've enjoyed the video, and